Okay, so let's discuss a question from thermodynamics. It's a common data question. So you have a piston cylinder device where basically you want to compress this adiabatically, and the initial volume is basically the 100 liters. So 1 liter is 10 power minus 3 meter cube. Basically 1 meter cube is 1000 liters. So this is 0.1 meter cube, and the temperature is given as 25 degrees Celsius. So that is, if you add plus 273, you get 298 Kelvin. Whereas the T2 is compressed to a final state where the temperature is 273 plus 200 plus 273, so it's 473 Kelvin. Now we don't know the final volume, that is what is asked, but it is asked that when can you have the minimum possible volume. Now obviously it is given that it's compressed adiabatically, so the minimum possible will happen when the process is reversible, right? I mean, as it is a process of adiabatic, so whatever the work done you are doing, it has to go to the entirely to the internal energy. So the work done, if there are no irreversible effects like friction, so the work done will be completely utilized in compressing the air, and so the volume will be minimum. So when you don't have irreversible effects, the process will become reversible because already there is no heat transfer. It's given that it's adiabatic. And under reversible, what happens is that change in entropy is 0. So if I use the TdS equation, the TdS is du plus pdv. Okay, now TdS is 0 because we are assuming that because for minimum possible value it got to be a reversible process. So du for an ideal gas, now air is assumed as an ideal gas, so du we can write mcv dt, and pdv we can write. Now actually, I mean, before applying this T, actually I can take T, before applying the fact that entropy is 0, I can take T right hand side and then apply the fact. So this is mcp dt, and I can just integrate as well. So that is like S2 minus S1, okay, and this is mcp ln T2 by T1 plus P by T ln V2 by V1. Now I think I wrote a couple of steps forward, but let's understand in this way. So this is S2 minus S1, and that is mcv ln T2 by T1, that is the process. Now P by T I can always write because it's ideal gas equation, so P by T is mRT. So P by T, because I need to, inside the integral I need P by T, so it is mR by V, and therefore when I integrate mR ln V2 by V1. So this is what I get. Okay, so basically m is common. Now Cv ln T2 by T1, so change in entropy is 0 plus R ln V2 by V1. Okay, so this is all about it. So now because we know the change in 0, Cv is given as if you look at the value of Cv is given as 0.718. okay, 0.718 ln T2 is your 473 by 298 plus R is 0.287 ln V2 by V1. So from this is just an equation ln, so you can just find out directly what is ln V2 by V2, and then you have to take exponential on both sides. So from this equation, if you calculate V2 by V1, I get close to 0.317, and so V1 is already 0.1, so I get 0.031 as the answer. 0.031 is the answer. So C is the answer for this common question. So it's a direct, only thing is you have to remember the TdS equation. Thank you.